Hello everyone and welcome back to the Jamaican Geologist YouTube channel. This is episode 17 in the Geology Foundation series, and today we are going to look at geological time. How do geologists know that a rock or mineral is millions of years old? What methods do they use? And what exactly is the geological time scale? We'll explore all of that and take a quick dip into some of the biggest events in Earth's natural history. This promises to be a fun journey, so let's begin. So, it's all about dating the rocks. And not taking them out to dinner or a movie, although a geologist dating rocks could make a funny little animated series. But fun and jokes aside, when we say dating rocks, we're really talking about two approaches: relative dating, figuring out what came first, and absolute dating, figuring out exactly how old something is. Let's use a family example. Imagine a brother and a sister. The brother was born before the sister, so he's older. That's relative dating. Now, if you check their birth certificates, the brother was born on March 4, 2010 at 1:15 p.m. and the sister on January 11, 2015 at 4:21 p.m. If we calculate their ages on September 28, 2025 at 2:20 p.m., the brother is about 15 years, 6 months, and 24 days old, while the sister is about 10 years and 8 months old. That's absolute dating, using actual numbers. So to put it simply, relative age equals what came first, absolute age equals exact time and date. So the same principle applies to rocks. Geologists use stratigraphy, which is just the study of rock layers. Here are a few key geological principles. Superposition. In an undisturbed sequence, the oldest rocks are at the bottom, youngest at the top. Think of it like a layer cake. Original horizontality. Layers of sediment are originally laid down flat. If they're tilted, something happened afterwards. Lateral continuity. Layers extend sideways until they thin out or hit a barrier. So basically, layers were originally deposited as continuous sheets that extend in all directions, remaining unbroken until later disrupted by erosion or other geological processes. Cross-cutting relationships. If one layer cuts through another, it must be younger. We also use fossils. Certain types of organisms appear at certain times, and we can use that to date the rocks. This is called the principle of fossil succession. And then there are unconformities, gaps in the rock record. For example, angular unconformity, which is like tilted layers overlain by flat layers. Then you have the disconformity, which is missing layers between two parallel sets. Then there's the nonconformity, when sedimentary rocks sit directly on top of much older igneous or metamorphic rocks. All of these help geologists build a timeline even without knowing exact ages. So basically, how old is one particular lithology or rock type in relation to the surrounding rocks. So stratigraphy gives us the order of events, but not the actual years. For that, we turn to absolute dating, especially radiometric dating. You may remember back in episode 3, we talked about protons, neutrons, electrons, isotopes, and radioactive decay. Well, this is where that knowledge really matters. Atoms of some isotopes are unstable. They change over time. They change over time by alpha decay, which is losing 2 protons and 2 neutrons, beta decay, in which a neutron turns into a proton or vice versa, and gamma decay, a high energy photon is emitted from an unstable nucleus. This lowers the energy of the nucleus so it becomes more stable. These are the 3 main ones, but there are others too, like electron capture, where the nucleus absorbs an electron. But anyway, each radioactive isotope decays at a constant rate, unaffected by heat, pressure, or depth. This rate is measured as a half-life, the time it takes for half the parent isotope to become a daughter product. People often think of carbon-14 as the main dating tool, but it only works for organic material younger than about 60,000 years or so. For rocks, we have many other systems like uranium-lead, potassium-argon, and rubidium-strontium. You can detect rocks in billions of years. So not all dating relies on isotopes. For example, there is something called dendrochronology, which is the study of the growth rings of trees. Each ring marks a year, so trees are like natural calendars. Then there is fission track dating, where tiny damaged trails left by decaying uranium atoms in minerals can be counted to estimate ages. Now let's put it all together, the geological time scale. This is Earth's calendar, broken down from largest to smallest. There are eons, which are the largest, eras, periods, and epochs, which are the smallest. Now then, the Precambrian is a term geologists use for everything before the Phanerozoic, and it contains the Hadean, Archean, and Proterozoic. The Phanerozoic is the more recent eon, and it contains the Paleozoic, Mesozoic, and Cenozoic eras. Now, the periods and the epochs are a lot to remember. Back in the day when I did my courses in paleontology, to remember them, I used the following mnemonics. So for the periods of the Paleozoic, I would remember the term COS-DCP. So it's Cambrian, Ordovician, Silurian, Devonian, Carboniferous, and Permian. For the periods of the Mesozoic, TJC is what I remember. So it's Triassic, Jurassic, and Cretaceous. And for the epochs of the Cenozoic, I would say a silly word, Piumph. So it's Paleocene, Eocene, Oligocene, Miocene, Pliocene, Pleistocene, and Holocene. So, and the time scale can get even more granular than this, with other subdivisions called ages, but for an introductory series, this is enough. So some key highlights in Earth geological history include the Cambrian explosion, where there was a burst of diverse life about 541 million years ago. Then there were the extinction events like the Permian extinction, the largest mass extinction in Earth's history, and the Cretaceous Paleogene extinction. That was called the Cretaceous Triassic extinction some time ago. But this is where the asteroid impact caused the reign of the dinosaurs to end, leaving behind the Chicxulub impact crater and a global iridium layer. Then there was the rise of mammals, which flourished after the KPG extinction. And then ferns were dominant in the Carboniferous, and trilobites are a major symbol of the Paleozoic, and we lost them after the Permian extinction. And we can explore these some more in other videos beyond the series. So why should we care about this? Well, because understanding Earth's timeline helps us see how life adapted to massive changes, from volcanic eruptions to ice ages. It also puts modern climate change into context. What humans are doing in a few hundred years is dramatically different compared to the natural changes that once took place over millions of years. So, there you have it, a journey through geological time. We explored relative versus absolute dating, learned how fossils and rock layers reveal Earth's story, and discovered how radiometric dating gives us precise ages. We also walked through the geological timescale and some of the most important events in Earth's natural history. In the next episode, the final one in the Geology Foundation series, we'll look at the Anthropocene, and I'll share what's coming next on the channel. So until then, it's bye for now. Take care.